And so good morning, good afternoon, and I've noticed from the participants, good evening. That's always nice to see we're going beyond just the Canadian borders. Welcome everyone, and today we have the honor and the privilege to have with us Dr. David Meyer from University of Toronto, Department of Civil and Mining Engineering. David will be talking to us about two topics that are super important, or one topic, which is intermittent water supplies, but in the context of megacities, which I find fascinating, and I'm very keen to hear. And without further ado, I'll hand the mic over to David.
Great, so let's get started. I'm just gonna remind you guys of a few things. One is you're here live, so feel free to turn on your video. I'm surprisingly engaging when I can see the people I'm talking to. So if you're falling asleep or confused, just turn on your camera and make like a face and I'll slow down or explain myself. You can throw your questions in the chat and I'm happy to try and follow it while I talk. Without more upfront process, let's get started. So I'm really excited about this topic. I became an assistant professor so that I could keep working on this topic. And we are talking about water distribution for megacities, and specifically understanding and hopefully improving intermittent water supplies. So we'll start with some, just briefly, like Caetano said, my name is David Meyer. I'm an assistant professor both in the Civil and Mineral Engineering Department at U of T and in our Center for Global Engineering. And for the past decade, I have been fascinated by intermittent water supplies. Oh, I see these cameras on. Thank you guys. This is fantastic. In today's talk, we are going to introduce intermittent water supplies, teach you the simplest ever way you could understand them, which is thinking about how one consumer would behave, quantify the reasonable accuracy that that one consumer model has to understand an entire network. And then we're going to use that model to show why satisfying consumer demand is this key component that we need to use and exploit to improve intermittent supplies. And then I'm going to demonstrate a method I think we can use to quantify what available when needed means in an intermittent supply. And then I'll end by giving you some tips and tricks about how you can use EPANet or something like it to model an intermittent supply, and give you a few more tips from my hard-earned lessons. So with that, let's get started. And Kelsey, please let me know if I've missed someone's hand, but I love that camera's on. Please continue. You guys are great. So some motivation. Our urbanizing world needs thoughtful, creative, global engineers. So McDonald and all did this really interesting study in 2014, where they looked at the amount of the land area of the earth that's covered in cities. That was 1%. So 1% of the dirt on our planet has a city on top of it. But those cities draw water from watersheds that cover 41% of our land area. So as we think about the future and urbanization, we are already drawing from watersheds that are almost half of the surface of the land area of the earth. And I think to continue to urbanize and to do that thoughtfully, we will need creative global engineers. And then on the right is a picture of the supply pipes leading into Mumbai, big city in India. And there are lots of people who do fantastic work on urban ecology and thinking about the metabolism of a city. But fundamentally, when you pile that many people in one place, they need huge energy and resource flows both in and out of the cities. And today we're going to talk about the water supply flows into those cities. So, the second way to motivate the talk today is with the Sustainable Development Goals. So at WASH Canada, you are no stranger to the Sustainable Development Goals, I suspect. Here is the map of 2021. I updated it this week. It's this year's data for what the world looks like in terms of safely managed water supply. SDG 6.1 is trying to hit universal and affordable access to safe water, safely managed water by 2030. And in 2022, we're missing data on more than 40% of countries. So on this world map, light gray means we don't know. We don't know what these gray countries have in terms of the percent of people who have safely managed water. Here's your refresher on what safely managed means or needs. The water supply needs to be on the premise. So in your front yard, in your backyard, or in your house. Why? Because then you'll use more of it and social marginalization can't affect how much you get. It has to be free of contamination. That's important. It also needs to be available when needed, because giving people empty water pipes is useless. You need water in your water pipes. And when you have those conditions, it counts as safely managed. So why don't we have data on these countries? We have data from nationally representative data. That doesn't mean we know everything, but we know enough to make a credible estimate for premise piping in 90% of countries. We know 60% of countries whether or not what percent of their supplies are contamination free. But we only know half of the countries in terms of whether or not they're available when needed. And this is the topic that relates closest to intermittent supply in the facets that I research. So that's what we'll be talking about today. So why is available when needed important? I kind of trivialized it saying water pipes need water in them, but fundamentally not all water systems are equal. In Toronto, where I'm based, the water system is on all the time. You can be 35 meters off the ground and still take a shower using the municipal pressure. A survey of 18 cities in India found that they averaged 4 hours per day of water supply. So the capital, Delhi, gives on average 1 to 2 hours of water in the morning and 1 to 2 hours of water in the evening. That system is also operating at really low pressure, which changes the dynamics as well. So you guys are here to learn about systems, but you also think about them already, I suspect. This isn't your first foray into this domain. And you guys are clever problem solvers or clever engineers. And so you can imagine if you were one of the 1 billion people on the planet who plugged into an intermittent water supply, you would find ways to make it better. So intermittent water supplies are not just an Indian issue, they are pervasive. Aaron Bivens in 2017 did a great estimate that suggested 1 billion people are plugged into intermittent water supplies, which means that 1 out of every 5 people on the planet that gets water from a water pipe gets water from an intermittent water pipe, which means improving them is key. So if you were one of these customers, one of these 1 billion consumers, you would adapt. And here are 3 adaptations I see all the time. On the left, we call them spaghetti pipes. If you live in a neighborhood with low pressure or not that much water, and you're not that far away from another neighborhood that has better pressure, maybe they're from a different segment of society, maybe they're just at a more favorable elevation, but maybe the chief of police lives there. Well, you could buy yourself a pipe at the market, and in the night, either yourself or with a plumber, run that pipe over to your neighbor's house and plug it into their water main that's serviced with better pressure. And then all of a sudden you've got lots of your water, so your neighbors think, that's great, I'll do it too. And then when you drive down the road, you see piles and piles of spaghetti pipes leading from a low pressure neighborhood to a high pressure neighborhood to improve the supply. I picked this particular picture because you can see that these pipes are right next to an open sewer. So we have this constant tension between water access and water quality. On the right, you see another classic solution. If the water supply isn't on all the time, you're going to store water because maybe you'd like to wash your hands or drink something when the water pipe doesn't happen to be filled with water. And so depending on your affluence level, you'll have more or less sophisticated storage methods, from using a bucket to having an underground reservoir to perhaps even a tank on your roof. And so your domestic plumbing system will be continuously operating. Well, so you basically use a capacitor or a storage tank to smooth out the on-off nature of the system. And then in the middle, one of the craziest components of some intermittent supplies is the pressure is so low that consumers plug in their own pumps to siphon water out of the system, turning customers from passive loads into active loads, reducing the pressure and perhaps actively pulling contaminants into the pipes. So consumers are great at adapting to intermittent water supplies. Why are they a problem? Well, fundamentally, the first problem with intermittent water supplies is water quality. So positively pressurized pipes push water out of their cracks. That's what keeps our drinking water safe. If you have a low pressure supply or a negative or an empty pipe, the cracks can go the other way and contaminants can intrude into the water pipes. And then when we turn the system back on, that wall of gross water that has filtered into the pipes overnight while they were turned off gets flushed through the system to those eagerly expecting consumers. You can imagine that if you have a tank on your roof, this big black plastic tank, and you fill it with the intruded contaminants that came overnight, it spends all day baking in the sun, and you get your own little bioreactor. So intermittent water supplies can allow contaminants to intrude, which compromises our water quality. They're also not very fair. They're not very equal. So this was some modeling work done by DeMarchis et al. In 2011. And what they compared in this map was the size of the dot is the ratio between the amount of water you got and the amount of water you wanted after 3 hours of supply. So if this system ran out of water after only 3 hours, the consumers at the black dots would have gotten more than 80% of the water they wanted, and the consumers with the kind of smaller dots would have less than 40%. So we see this spatial unevenness and unfairness baked into the network, both because of location and elevation. So improving intermittent supplies is really important, but it is not easy. So I don't know what else is going on in your day, but I hope that none of you have on your to-do list to make the calibrated hydraulic model for the network photo that pictured here, right? This would be impossible. Yet in our traditional kind of top-down engineering mindset, what we like to do is know everything about the system, calibrate our mathematical models, and then be able to predict the future, right? We talk about this digital twin between the real world and the hydraulic world is kind of the new frontier in municipal engineering. There will be no digital twin for this picture. Priya Sangameswaran writes beautifully about neoliberalism and Maharashtra's water supply reforms. And she critiques that the current method of improving water supply networks requires near perfect knowledge, which is totally at odds with the chaotic arrangements that actually characterize Indian cities. This is not a critique of Indian cities, but it would generalize to most intermittent water supplies, to most megacities around the world. They are growing rapidly, and the chaos associated with that growth is kind of an affront to our traditional, we must understand it before we can improve it, engineering paradigms. So what can we do? Aristotle might recommend that we look for the precision in each class of things just so far as the nature of the subject admits. And I would submit to you that the nature of the subject in this photo suggests that we better do something pretty simple because of its chaos. So what I want to tell you about today is the simplest ever model for an intermittent water supply. It has only one consumer. The consumer has a storage vessel, perhaps a bucket, perhaps a tank, and the pipe leaks, because these are the two fundamental components of a water network. There are some leaks and some consumers. Consumers don't just store water, but eventually if their storage becomes full, they stop storing water. And so here depicted in that picture is the icon of a tap. To make it more intuitive, I'll show you a picture of a tank with a float valve. So if you've never taken off the back of your toilet, it perhaps, if it's old enough, has one of these big mechanical float valves. When it floats up, it turns off the water pipe. And so this is going to be the kind of picture I use to represent an intermittent water supply. And hopefully it helps kind of visualize whether or not a consumer has received enough water to be happy or satisfied. So with this model, we'll go forward and say, what can we do with this? How does a one consumer intermittent water system behave? Well, the leaks in a simple system with constant pressure come out at constant pressure at a constant flow rate. So then the longer we let it leak, the more water we lose to leakage, right? If you go from 4 hours a day, from 2 to 4 hours a day of supply, leakage doubles in the short term, all else being equal. From 4 to 8, doubles again. 8 to 16, doubles again. What about the amount of water received by consumers? If you only give everyone in your network 10 minutes of supply, no one has enough. So if you leave it on for 20 minutes instead of 10, everyone would like double what they just got. And if you go from 20 minutes to 40 minutes, that's probably true again. But somewhere, when you go from 20 hours of supply to 21 hours of supply, most people's swimming pools are already full. And so somewhere on this curve, consumers become satisfied and their tanks are full. And so this was my big idea behind this model, is that there are two regimes, one where consumers are filling their tanks and one where they're pretty happy. And so if we put on our top-down kind of water utility hard hats on and say, how much water do we need to put into this network? Well, it simply becomes the superposition of these two piecewise linear curves. We need, for every liter we lose to leakage or liter that goes to a consumer, that's a liter of water that needs to go into the network. And here's where the model gets interesting. We can now study these two sections of there's two very different regimes. And we can use this model to probe the causes of intermittent supply and perhaps opportunities to improve them. So if you're operating a water utility and all you have is that dashed blue line of water availability, you have an intermittent water supply. Your intermittent water supply cuts off at time t. Maybe that's, I don't know, 10 hours a day of supply. If it gets to be the dry season and you have less water, you still have the same pipes. They still leak at similar rates. You still have the same consumers. But all of a sudden you have way less hours per day of supply because of a source water change. So these two regimes, kind of the steep slope area and the shallow slope area, are the key features I want to spend a good chunk of time today talking about. But before we talk too much more about this model, you ought to ask yourself, why would I care about a one consumer model? No one has a one consumer intermittent water supply. Is it accurate? Should I trust it? So to test this in my research, I compared it to a numerical simulation of a physical network inspired by the Modena network in Italy. It's one of these free EPANet models you can download. It's a continuous water supply. So to make it an intermittent water supply, I gave every consumer tanks and some leaks in the network. And when you simulate it spatially and temporally. So it's changing over time and space. And you can watch consumers go from yellow, less than not having enough water, all the way to blue when they're happy. And now we can ask, how did that network perform? So this is the numerical results from that simulation. Is it a piecewise linear? No. Is it a whole lot like the straight line model I constructed with you guys? Yes. And in fact, it was surprisingly accurate. I got an R² after calibration of 0.98. So almost all of the variation in this model is explained by the piecewise linear behavior of a one consumer intermittent supply. So that gives me reason to think we should probe this simple model to use it to learn about intermittent supplies. And so if we do that together, what I would like to suggest is that improving, I'll call this green region, where the black line is pretty shallow and consumers have the water they want. I'll call this a satisfied intermittent supply. And I would suggest that improving intermittent supplies like this is hard, but feasible. So in this example, the intermittent supply operates for 12 hours a day, but consumers would be satisfied if they got anything more than 6. So you're running this utility and you want to fix the network, or you're at a donor agency and you're trying to figure out how much money should we allocate to try and help this city improve their water supply. Well, in this type of water supply, if you found and fixed leaks in your network, so you went from the solid orange line to the dashed orange line, you could change the black curve and run your city 24 hours a day with the same amount of water, because for every liter you no longer leak, that's a liter, well, as you slow down the flow rate of your leaks, you can leave them leaking longer. So we can achieve 24/7 in these systems by leak repair alone. But there is a harder part of this story. If you are working with an unsatisfied intermittent water supply, they're really hard to improve. So in this example, the intermittent supply operates for 2 hours a day when it would take 6 to satisfy consumers. So to make this, I'm going to stretch this graph out to be from 0 to 6, not 0 to 24 on that horizontal axis, just so you can see what happens. And what happens here is that if we like that blue line is our water availability. And so if you pay a public agent, if you pay a water utility or you privatize your network, your private operator is going to spend a lot of money finding and fixing the leaks. And if they find and fix every single leak, you can increase your supply hour. But you probably did not fund this project expecting to go from 2 hours a day to 2.4 hours a day of water supply. You would have spent millions of dollars finding and fixing leaks, arguably for naught. So only a small increase is possible with leak repair alone in this type of intermittent supply. Even if it's a really leaky intermittent supply, it's like 40, 50% leakage. When you fix all of those leaks, you still can't satisfy your network. And so this type of intermittent supply is much harder to improve. And I think it needs different planning tools to, I think we need to be more realistic about the projects we set up in these systems. Because we certainly shouldn't be spending a lot of money to find and fix the leaks, believing that will be the mechanism by which we achieve continuous supply. So I've used this model to argue there are two types of intermittent supplies. Very hard to improve intermittent supplies, where at the end of the supply, customer tanks are still empty. If you gave them more water, they take more water. And the everyday kind of just hard to improve intermittent water supplies, where at the end of the supply, consumers are satisfied, which means the leak repairs are an efficient lever to pull. If you want to read all about the calculus and the model behind this, there's some links in the slide deck. But I want to focus on the implications, because this isn't a theory talk. This is hopefully some more implications. The first thing I think we need to be really clear about is that demand is what consumers want, not what they should want, not what public health guidelines suggest we should give them as a minimum. So for example, if your standards manual suggests that you should provide 150 liters per person per day to everyone in a city, if you happen to be supplying to a neighborhood where people, for whatever reason, haven't read that standard manual and would like 200 instead, then you're in this setup with the blue curve and the red curve, and you will have an intermittent supply. An unsatisfied intermittent supply, simply because you have failed to account for how much consumers actually want. Too many projects are designed based on textbook values of demand rather than measured or realistically projected demand values. And I think this is especially an important problem in kind of the increasing focus on rural piped water supplies, where we have these standards for rural supply that are much lower, like 40 liters per person, 50, 55 liters per person. And if we build those networks, they will be intermittent. Anytime consumers want more than that theoretically required minimum. So to pick on a specific example, Moody is doing a fantastic big or an enormous infrastructure push in India to get every household piped water. So the slogan is in every house a tap, in every tap water. By 2024, I downloaded the dashboard this week. In the last few years, it's gone from 17% piped access to 47% piped access. Huge infrastructure push. But the funding mechanism will only support a piped water network if it provides a maximum of 55 liters per person per day. Which means these systems are guaranteed to be intermittent anywhere people want more than 55 liters per person per day. So was that number informed by some sort of equality aspiration? I think so. But if we're going to be building pipe networks, they need to be built not for these kind of minimum public health values, but for minimum demand, for projections, realistic projections of how much customers actually want. So I've argued that these two regimes are really important. The next thing to tell you about is how you could ever tell which regime you were in. And here is one of the most fun parts of this simple model that I found, is that when, let's put on our consultant hats. Someone flies you into a city, it's an intermittent supply. You don't know whether it's satisfied or unsatisfied. You don't have customer data, you don't have anything. What I would suggest you do is, your system could be at T1 or T2, but you don't know where this inflection point is. And so the method I would recommend is that you ask your partner utility to make small changes in their input volume. So, for the first week, don't deliver quite as much water as you usually do. For the second week, deliver a little bit more water than you usually do. And what that's going to do is it's going to give you the gradient, the slope around your normal supply timing. And if you take that slope and you project it over to your y-axis, you get the purple dot. I'll save you the calculus, we'll call it purple dot. And in a satisfied intermittent supply, the purple dot is the same as your demand. So when that intercept is equivalent to the amount of water your consumers want, it's a satisfied system. And if you run that exact same test procedure at T1 in the unsatisfied system, purple dot goes to 0. So all of a sudden we have this huge shift depending on which side of that inflection point we're on. And in the piecewise linear model, it's nice. It's either exactly the demand or exactly 0. In the real network, it's not quite that. It's a curved line that gradually varies from 0 to 1. But I think this idea can still give us a % satisfied estimate for a network to help us understand to what degree is this complex network best represented or characterized as a satisfied or as an unsatisfied intermittent supply. So why are we doing this? We began with this idea of available when needed being a critical component of our Sustainable Development Goal 6. If you read some of the documentation as the United Nations has articulated the human right to water, that water supply or that water source needs to be, quote, continuous enough. That makes sense from a policy perspective, but from an engineering perspective, that's quite difficult to measure. In our JMP data, we're using surveys asking people, is your water available when needed? National standards, and as a backup, 12 hours per day is the global benchmark for how long it needs to be on to count. I think we can do better. If it's true that intermittent supplies have these two regimes, satisfied and unsatisfied, this green regime is by definition the regime in which customers get or consumers get the water they want from the network. And I think that's what we mean when we say available when needed. And if that's what we mean when we say available when needed, we also have a way of measuring it. That method I showed you on the last slide of purple dot over demand gives us a proxy for the degree to which our complicated intermittent supply is well represented or for the most part is available when needed. So this was the big idea on how to understand and potentially how to improve intermittent supplies. The last few things I want to do are just share a few tips and tricks I have for you in order to think about and potentially improve intermittent water supplies. So when you're modeling an intermittent water supply, I tend to use EPANet because it's free. My recommendation is that you aim for a model that's good enough to be useful. As I said, you don't want to have to calibrate it. So initially neglect your filling and draining states, model your steady state. And for every node in your EPANet model, that's usually how you represent demand, add some leakage. Leakage is really important in intermittent supplies. And represent consumers with a tank that's connected with a pipe with friction asterisks. There's a lot of debate about the appropriate amount of friction on that pipe. I've put some papers here, some by me, some by others, that kind of debate about how to best represent the connection between that consumer tank and the network. But fundamentally, I think this is the easiest, most useful way of representing, at least initially, how an intermittent network would behave. And when you do that, you get videos like the one I've showed you before, where you can watch how water is flowing through your pipe network, and you can model how different, you can model how different tanks at different times are filling, right? So you can say like, oh, actually, after 7 hours of supply, this many consumers have enough water, and so on and so forth. Susan, I see your question in the chat, and I'm almost done, so I'd love to come to it just after my conclusion, but thank you for throwing it in the chat. So that's how I think about intermittent supplies, and that's the same method I use to validate this model. And if you've got your thoughtful critical hat on, a lot of the assumptions behind my model and in the modeling method are similar, which is perhaps why they align so well. But we can talk about that in the Q&A if you want. My other two practical tips before I just show you a conclusion slide is one, measure leakage, at least on a per hour basis. There's a lot of unknown in intermittent water supplies. And so the utilities you may be working with or interviewing or studying likely have some averages or some assumptions in their model. And so Delhi might tell you, Delhi, India's capital, might suggest they have 40% non-revenue water or leakage, which means that's 10% per hour of supply. So if they're losing 10% of their total water volume per hour the system is on, how much water would they lose after 10 hours of supply? Well, it's kind of a math conundrum because you can't leak 100% of your water, and the math gets a little more complicated if you want to keep the percentage of total water. But fundamentally, to stay on 10 hours a day, Delhi would need to leak 100% of its current water. So why is it an intermittent system? There are many reasons, but measuring leakage on a per hour basis will help you figure out whether leaks are one of them. The second thing is I've spent a lot of time in my research thinking about consumer suction pumps. These pumps people are using to pull them out. I've got a new paper that uses a pressure sustaining valve to try and fight them. But one of the stories I wanted to tell you is that where these suction pumps are most problematic, their removal is most contested. And where their removal is most feasible, their effects are most small. And so it's not often a low-hanging, high-leverage intervention point to tackle the suction pumps first. It's kind of a hard-learned lesson I've had recently. So fundamentally, I'll tell you what I told you today. We talked about improving and understanding intermittent water supplies with these two kind of models of an intermittent water supply, of what consumer tanks would look like when the system turned off. They're either empty or full. And talked about how this unsatisfied versus satisfied regimes can help us think a lot about how we could or how feasibly we could improve an intermittent supply. I showed you some hand-wavy validation data from the Modena network. Showed you some tricks you could use to model an intermittent supply in EPANet, and then concluded with some other tricks on thinking about the importance of leakage on a per hour basis and why I wouldn't recommend you start by focusing on consumer suction pumps. So my email address is there. I've been funded by a lot of people over the years. I'm currently at the University of Toronto in our Center for Global Engineering and Civil and Mineral Engineering. I've been funded by the Tata Trust, the Tata Center for Technology and Design at MIT, and by NSERC. So I would love to hear your questions, your concerns, your collaboration ideas. You've got data that proves me right or wrong. Wrong is even more important. Please email me or let's chat. So thank you very much.
Well, David, that was fantastic. I love your energy, and I have to admit, as a water treatment person, my attention for hydraulics seminars is sometimes intermittent, and this was anything but. So thank you. This is awesome.
Excellent. Thanks.
Anyway, I think we already have a question here in the chat. Do you want to take it?
Sure.